speaker we have is with us Nicolas Boeckh. He's a software developer, and he is going to discuss the topic on securely storing and transmitting information on mobiles / IoT, a story in development. So, Nicholas, it's you now. Thank you.
Right. Give me a second. Poof. And let's do this. Fantastic. Let's remove that. Okay. Hello, everyone. My name is Nicolas Boeckh. Thanks for joining me.
Hold on. Let me set up one thing, Nick. Sorry for interruption. Ivan, can you check camera for Nick, please? Yep, it's coming up now. Good
Perfect.
to go.
And yeah, so thanks for joining me at Besides Islamabad. This is going to be a high-octane roller coaster of InfoSec, DevSec, and IoT. The title of the talk is Securely Storing and Transmitting Information on Mobile / IoT Devices. And it's a story in development. It's from a development perspective. So who am I? Well, I usually go by Atomic Nikos on social media. You can find me on LinkedIn, on Twitter, I have a blog, on GitHub, on GitLab, etc. I am pretty active, at least in the field of development. I've been getting more active in the field of information security and OSINT, and that's part of my perspective in my talk today. So when we're talking about cybersecurity, which isn't entirely the topic of this talk, we're talking about a world, an entire world. And the main issue I have when seeing this world is that when we're discussing development security, well, development is a process. It iterates over time. You have multiple phases. And when you think about it, not one single aspect of cybersecurity does map to development security. And so what I'm going to do is I'm going to bring you from the overview perspective of cybersecurity into the nitty and grainy perspective of everything that development security DevSec touches. So from this map, I'm going to define a small color scale, which goes from, which represents ideation, development, production, deployment, incidents, which are the multiple phases that a project can go through, sometimes multiple times. Where ideation would be when your idea takes fruit, when your idea is born, someone has an idea, of how to implement said idea, thinks about certain protocols that they want to implement, stuff like that. Development is when they put the building blocks together, of course. Production is when they start, discussing it with their user base, training their users, putting it out there, basically, quote unquote. Deployment is when it's fully out there. The clients or the users have access to the platform, to the service you provide. And typically, it's not something everyone does, but we do factor in incident. Incident being the moment where something goes horribly wrong. So if we start at ideation and we use our map from earlier, it hits a ton of places on our cybersecurity map. So here in ideation, for example, well, you do need to have a certain idea of the laws and regulations in place. For example, you do need to be aware of data protection and how that will factor into your security architecture, for example. If we move on to just development, discussing security architecture, how you manage access control, how you perform risk assessment by doing source code scans and the like, is also some things that will only happen in certain stages, like this one. When you're in production, well, you start getting some more security operations. You start discussing some things like threat detection, threat protection, etc. And you also start to educate your users by training them their new skills or making them aware of issues that they can be exposed to. In deployment itself, you stay pretty much on the same thing, but you do have to maintain your assets inventory. You do, at some point, probably will have to have some form of penetration testing on your service, and all of this does impact you. Finally, you also have, well, the moment of the incident when an incident response happens, an incident happens, incident response goes into play, and you have all these things like breach notifications, incident containment that all factor in. And that's a lot of things we just talked about. So I just pointed out a few just on the map, and I'm thinking of a common point. What is that common point? Well, it would be contentious to say developers. I'm going to say developers, but I'm going to say not only developers. It's developers, managers, and the entire rest of the hierarchy. That's very important to think about. There's not one single point of failure, not one single point of blame. Why am I giving this talk? Well, I'm a developer first, and I do have a few fingers in the InfoSec pie. And so I'm InfoSec adjacent, I would say. And that's something that not everyone is. Usually you will have developers who are InfoSec aware, that have some knowledge of how to secure their stuff, will be able to do the research to additionally secure their services. But the scariest part, and the one that happens in most big companies, is that you have developers that have no clue of how InfoSec works, or anything that they would do in InfoSec. And that is something quite scary that can lead to issues such as there being an entire divide, a big gap between your developers and your information security specialists. The second reason why I'm giving this talk is, well, I'm a student. I'm doing a bachelor's degree in information systems and service sciences, which basically breaks down into development, management, ethics, security, and regulations on a big ball. Well, to be fair, it's not an entirely equal ball. I do way more development than I do management or security, which is what led me to practice InfoSec and OSIN on the side. So what are we going to talk about? Well, I wanted to basically do a small brief overview of the ecosystem, basically ground some terminology first. Right up. Then I wanted to discuss why we would want to do this, the people involved, the technology involved, how those two produce risks when combined, and the fallout that can come out when those risks aren't taken care of. Then I'm going to discuss some risk mitigation, and finally go a little bit live at the studio with the development team and their managers, which is basically back and forth of things I've already heard and things I should have said at the time. Things that will probably make you scream. So first we're going to talk about IoT, the Internet of Things, what it is, mobile devices in development, what is information transmission at the base level, what is information storage at a base level. And since these things kind of build up on one another, I'm going to start with information storage and end with IoT. I hope that makes sense. So information storage, very quickly, it's bits on some form of storage, which would be flash memory like SD cards or SSDs, hard drives. It can be live memory, such as in RAM, stuff, things like that. It's stored in certain forms, such as raw data, which would just be like device output, sensor output, or process data, which would be some text files, CSV files, JSON files. They can be more or less hierarchical and more or less useful. Now that we have some information, we can actually transmit it. Well, one thing that's pretty often used to represent physical devices placed in a network and what data can flow through and how it flows through is the OSI Stack, which is multiple layers, which go from the layer 1 physical layer to layer 7, which is the application layer, 7 being the closest to a user, 1 being closest to the hardware. If I clean that little tweet up, it kind of looks like this. And this would be, for example, a mobile device like a smartphone. And if I were to connect it through a router, your router would be a physical media, which wouldn't have all of your application layers. The problem being is we're also discussing IoT, and IoT devices will have a peer-to-peer connection usually, and that connection will have multiple layers, not necessarily all 7, but will have multiple layers more to interact with. How does information go through? Well, you have some snazzy packaging, quote unquote, where PDUs, protocol data units, are used to package your data much like a letter. For example, in the Ethernet PDU, you would have a destination address, which is where your letter is going, a source address where your letter is from, so that if it doesn't get there, it can ping back or whatever. The length of the content, which in this case isn't. The FCS, so that would be an integrity check code, often a CRC, a cyclic redundancy check, and some flags, which would be your postmarks, for example. So mobile devices and development. So mobile devices themselves at a base level, they just store and transmit information, and they enable some form of user interaction. Oops. Development in itself can specify additional requirements from a more abstract perspective. For example, requiring the use of Bluetooth, requiring the use of databases, requiring access to certain files, to the internet, to an API, things like that. And for that, you use development stacks. I just highlighted a few. You have a few native ones for Android, for example, Kotlin and Java. For iOS, you would have Objective-C and Swift. One is more recent than the other, of course. And then you have some things in the middle of Android and iOS. They do cross-OS development. For example, Flutter and React Native, which do these kinds of fancy things. So now that we can talk about IoT, what is the Internet of Things? What does it include? Smart everythings. What is a smart everything? Well, think of fridges, watches, cars, smart homes. If you even want to go that far, we can even talk about teledildonics. So things like IoT butt plugs and stuff like that. SME actually did talk about that at DEF CON 27, and it's pretty fun if you just want to look at it. When we're talking about IoT, we're not specifically talking about all this. We're talking about a cluster of IoT devices. And that cluster is usually service-centric. Think maybe an IoT sensor grid that measures carbon monoxide levels on city streets. It's my go-to example. These IoT clusters kind of form the IoT Triad when put in conjunction with mobile devices and servers. They have multiple ways of communicating. You would have, for example, Wi-Fi or GSM networks between phones and servers, or between IoT devices and servers if you have fancy GSM capability on your IoT chips. You could also have LoRa, which is long-range radio frequencies, where you could just transmit from an IoT device straight into a server that has the correct add-ons, quote unquote. You also have Bluetooth and NFC, which can be used to transmit information, although maybe slightly less fast. So why would one want to do this? Well, as I said before, we're going to go through the people, the technology at hand, the risks that both of them produce, and the fallout that happens when you don't take care of this. So quick overview of people. You have users, which if you're building a service goes from they're your best friend because they give you money, and they're your worst enemy because they bring you problems. We've always, most of people who have at least manned a help desk for 30 minutes will see that, or I don't know, a ticket system in some type of service, will know that there's that one type of user that always has 50,000 types of problems, which are improbable to say the least. So yeah, the basic morality is to love them for the income and hate them for the problems. But they're not the only people involved. As I said before, you have developers and managers. And well, at some point in the hierarchical chain, because everyone manages everyone, you have people that will just let something burn off to save face. And that is an issue because, well, at some point you are also responsible, and they might just shift the blame onto you. So it's better to do things that are solid. Now, if we talk about the technology, well, in some shape or form, it always boils down to information storage. Whether you're talking about IoT devices, databases, data dumps, servers, log files, or even APIs, it all relies on some form of information storage. IoT could be storing sensor output for a certain time. Databases will store data. Data dumps will be a representation of data that was stored. Servers will contain files. Maybe a web server will contain also your web pages and stuff. And these, if they're exposed, can also, have some information in them. Log files are pretty juicy usually. APIs, if they're too chatty, you can access the content within without too many issues. And all of this relies on some form of physical media, which is the main flaw with information nowadays. Is if you have access to a hard drive, well, either you have a very good encryption, which is fun always, but it won't hold up to a threat actor, as a state level threat actor. When we're talking about information transmission, well, it usually goes through some form of medium. Wires, for example, Ethernet wires, USB cables, etc. Bluetooth, which would be proximity wireless, think also NFC, or Wi-Fi, which would be longer range wireless. Think maybe also LoRa or things like that, GSM networks. An important part of information transmission is the availability. Usually when you have an information provider, quote unquote, you expect the information to be available 24/7. If you have downtime, it's an issue. And that's something that factors into technology. Finally, you have protocols which assist the transmission of information. There are multiple protocols that handle authenticity, for example, that the person who sent it is actually the person who sent it, that the origin of your data is the one that it really came from. Authentication, which would be that the user that sent it is allowed to send said data. Integrity, which would be that the data wasn't modified over time. And security, which many people don't do, which would be maybe encryption or things like that. In terms of IoT, over the years, no, this isn't a fixed number. It defines what you define as IoT. The number of IoT devices in the world, it's not 50.1, it's not 50.1 million, it's 50.1 billion. If I just compare this graph also, which doesn't say the exact same, well, actually, yes, it does say almost the same numbers. Many things are IoT, and many of these things, especially the entire yellow and gray area, these ones here, this entire area is IoT, such as maybe smart plugs, it can be printers, it can be anything. And those are the ones that are usually most vulnerable, and there's a ton of them in the world. So yeah, my main conclusion on the technology is that it's a huge attack surface. Now, when we talk about risks in IoT, now that we've talked about technology, the one main rule is that the S in the terminology of IoT stands for security. That meaning that there usually isn't any security. In terms of storage, well, usually your IoT device will have an SD card. An SD card is pretty simple. You just take it out, plug it into your laptop or into an adapter, and poof, you have physical access. It's pretty easy I/O. It contains files. Usually sometimes files it shouldn't contain, and that's an issue. Second point of note is microprocessors are on these machines. And if you know what you're doing, you can actually retrieve the bytecode, the assembled code on your microprocessor. And even if you're not going to reverse engineer it, what you're going to do is maybe find some static values like API keys and stuff like that. It's pretty dangerous. So yeah, if it's addressable to a computer, it's addressable to you. You just need to have the right tools. Thanks to Blind Hacker for actually giving me that quote. When we're talking about transmission, well, we're talking about Bluetooth Low Energy. At the base level, it's just a plain text byte stream that goes over some networking protocol. It's vulnerable to passive observation, observer in the middle. It's vulnerable to actual physical attacks. For example, by leveraging the GATT framework, so generic attribute, which is how they segment their data. For example, using services and characteristics in Bluetooth Low Energy devices. And fun thing is that there's no standards, but they have built profiles for Bluetooth. meaning that interoperability between these devices, and that's also an issue. For example, tautology not. So one of the pen test partners, a UK firm that does pen testing, did an entire thread about hacking a smart lock, which had Bluetooth Low Energy, and it was ridiculously easy. If we're talking about long-range RF, well, it's also plain text byte stream, except it's over radio frequencies. So you have the right receiver, poof, you can receive your data. Wi-Fi, well, that's not my area of knowledge, quote unquote, but it is vulnerable to packet capture and all that, those other risks. In terms of storage itself, well, on mobile devices, storage has also usually, if you're one of the 90% of devices that support SD cards, well, SD cards, you can pretty easily get them out of a phone. You can pretty easily get them into a computer, yet again. And also, it's not just one or two files, it's all the files. It can be anything. It can be badly cached data. It can be just a data dump that an app is keeping on the side. It can be anything, and that's even more dangerous. If you think about rooting or jailbreaking your device, depending on if you're Android or iOS, well, that gives you access to cache data. Cache data is usually where, the apps hide all their fun stuff. Even if your phone isn't rooted, well, you can use apps like My Phone Explorer or iMazing to just get at least a certain level of information. What I like to say is that even with the most recent legal issues between Epic Games and Apple, where children or players of the video game Fortnite would have to jailbreak devices to be able to install Fortnite on iPhones, well, is your 8-year-old really part of your threat model? If not, he should be, but well, they should be. In terms of memory, which is also a form of storage, well, you have concurrency issues. The paper I linked really goes into depth about how concurrency issues can produce funky and destructive results on a phone. That's something to take care of and to think about. In terms of transmission, well, the usual Bluetooth Low Energy, Wi-Fi, etc. NFC, so near field communication, is vulnerable to skimming. You can put NFC skimmers on bank terminals, stuff like that. Well, more usually on terminals at shops and stuff like that. And you can just skim some credit card details and reuse them. So that's fun, I guess. In terms of risks, well, you have services on phones. Your phone usually gives you access to geolocation. Some sensors like gyrometric data, electromagnetic fields, luminosity, stuff like that. The paper I linked produced an app that was able to determine with 88.8% probability if you were sleeping based on that sensor output, which sounds fine until you learn that, these apps can be hijacked and, well, maybe I want to, rob someone and, oh, they're sleeping. Perfect opportunity. In terms of service, well, that's yet again not my area of knowledge. Here's a video, a link, which might be fun for you. Honestly, it's not my area of expertise, so I'll defer to those and the internet. Let's do a small story about IoT. Well, let's talk about IoT smartwatches. There's these kinds of IoT watches that allow you to track your children, which sound fantastic. So a Dutch security company bought one for their child, quote unquote, registered it and installed the app. What they then saw is that there was some communication between the app and servers. So they installed Burpsuit, which is web application pen testing tool, in the middle, and they would see that the app was using an ID to query the server for the location. So what they do, well, they changed the ID and the location changed. They tried to replicate this in a browser. That didn't work. So it was more of a case of a sufficient level of authentication, but not of authorization to data that was accessed. And this gave them potential access to 100,000 of children's locations, which is a huge issue. Now, thankfully, that issue, which implicated a third party, has been fixed. But it's just, it quantifies the risk. In terms of fallout, well, you can quantify fallout through multiple metrics. For example, the amount and sensitivity of the information that was exposed, how the controlling entity responded, so that would be the company that owns the service, for example, and how fast the service recovers. If you don't have, if too much information was exposed and the entity doesn't respond correctly, you erode the trust in the service. If you have information that's too sensitive and your service recovers slowly, well, your feeling of privacy might be eroded. And if your service recovers slowly and your entity responds horribly, it also erodes the credibility of the service. And if you have the Magnificent Three, you have something called an omnishambles, which is a situation that has been comprehensively mismanaged, characterized by a string of blunders and miscalculations, which is a polite way of saying clusterfuck. And if you have that omnishambles, well, that gives the big C's of your company an opportunity to yell. I'm going to go through a live example. Lisa Forte has a series called Rebooting, where she talks about cybersecurity in general. And they did a hypothetical scenario for a dating company called Right Match Singles with some high-level people on it, some celebrities, for example. And they have a massive breach that compromises users and personal documents that shouldn't have been stored there. They failed to disclose it properly to the relevant British authorities, which would be the ICO, and also to its users. And finally, once they get threatened with legal action because it gets out, well, they go nuclear and just take the service down, which is a big issue. This checks all of the boxes from what I was talking about earlier. We can quantify fallout just by how the entity responded. For example, if you have information disclosure in some new service part, and it's solved pretty fast, gets a good payout for the bug bounty, poof, that's fantastic. If you have a user information disclosure in some forum or whatever, and it takes a while to get solved, let's not talk about the payout, that's okay, it's still solved. But for example, when we talk about Giggle HQ and digital interruption being a pen testing and cybersecurity firm, group, Giggle is a company that produced an app called Giggle, which allowed people, well, mostly women, to communicate between each other securely. And they were extremely leaky in the information that their API could provide. And so Digital Interruption contacted them, and they were like, no, we have no issue. And then proceeded to antagonize the InfoSec community, which didn't work correctly. It actually turned into a dumpster fire. So yeah, fun. Let's talk risk mitigation. How do we reduce the risks of getting punked? Well, in terms of IoT storage, avoid upstream critical files. You wouldn't believe the number of SSH files or things like that I've seen on IoT devices, just so that they can do firmware updates and stuff like that. Try going for operations logs instead of full data logs. Operations logs logging state changes in case of general usage, and state description, an error description, and the data that produced the error in case of an error. That actually first keeps your memory impact smaller, but also produces less information that an attacker could use. And also don't produce anything that can't receive firmware updates, because even though your device is secure now, that's not a guarantee in the future. So yeah. In terms of transmission, well, you can define and use standards for PDUs, so protocol data units, what we talked about earlier. You can use standard representation for data, like the IEEE 754 representation for floating point numbers, the default binary representation for integers, characters, etc. What advantages do they have? Well, if you have a standard, you can most probably detect some form of error or modification. And also, it also usually compresses the data. Like floating point numbers are 6 characters, which is 12 bytes. The IEEE 754 representation is 4 bytes only, and that's smaller. Some bonus points go towards an extensible framework. Like you could be able to add stuff over time without it crapping out, validating the integrity of your data, adding timestamps to avoid replay attacks, stuff like that. For example, here's a custom clear text transmission PDU. which would allow you to send data over Bluetooth Low Energy. So this isn't secure, but at least it has integrity. For example, it stores 2 flags, the length of the number of values that the entire map should have, a map of all values that are actually in the values array, and then the values. Finally, it just adds a small CRC at the end. So I'm going to take that very basic example and go into a practical example. And we're going to talk about an IoT pacemaker. Transmits vital information to the phone. For example, for if you have tachycardia, it should be able to call an ambulance or stuff like that. So the phone monitors for variations in your heart rhythm, tachycardia, etc. The information that's sent from the device would be the device ID, the heart rate, ECG values, EGG values. All these things are used to monitor heart activity. And the information received by a device would be should defibrillation occur, and also the power of said defibrillation. So the risks are, well, induced tachycardia, then death. Sounds fun. So how are we going to go through building that? Well, we can coalesce data, transform that data, map that data, encrypt the data, check its integrity, and then finally set flags. Now let's do that step by step. Coalescing data. So I just took some random data. I took a device ID, ICD_1337, this random heart rate, which seems normal. I think it was my heart rate at the time. It's a little bit higher than usual. Stress. ECG values, usually there's more of them, but and EGG values, usually there's more of them, but it needs to be a legible example. So, right, I forgot I had these things. So let's transform the data. So our device ID, well, it's a string. How can you represent string? Well, with cars. But how do you know that your text is going to be a certain length? Well, you use a flag. So here we use OX0D, which isn't the character that is really used unless for carriage returns and stuff like that. You store your text size, which would be 8 characters. You then store your text, which would be a certain number of characters. And then you finish with another text flag. This gets you a device ID, which has a text flag, a length, the data, and then finally another text flag. If we talk about the other information that was there that I talked about, well, that's an integer representation. Those are multiple integer representations, and we have an empty data, which can happen at some point. So we just replace it with X's for the moment, and then we add the rest of the data around it. Then we map the data. So we have 8 values in total, and we have our before last that isn't there, the 000 one, well, the X's that we saw earlier. So the map data would be this, because you have 8 values. Your zeros, your empty values aren't mapped, but you're keeping that entire value here. Then you add your device ID, then you add your values. Magic, quote unquote. So let's go to encryption. So for example, we could use a ES 128-bit in CTR mode. Fun. So here's some keys and some IV initial vectors. And I use CyberChef because fun. So your unencrypted data turns into this. Fun also. You can check for integrity using your CRC16, for example, in ARC mode. The output of said CRC would be 4655, no, 5F in hexadecimal. So here we used another tool. So your encrypted data generates that CRC. And I forgot to change my output, my bad. So the final iteration of your data would be this. And then you set flags. The main issue being that flags, if you've studied Ethernet, they have a certain structure, and that structure can also be found in other places. So what you do is you check, for example, this is 6 consecutive ones which define a flag. Well, here you check for 5 consecutive ones, and every time you find one instance of that pattern, you add zeros right after them. This is something you then can remove pretty easily. So now that you have this thing with added zeros, you transform it, to the hexadecimal representation. You add your flags, does this, and that's the data you send. So now we're going to evaluate the solution. In terms of compression, well, you go from a certain level of text. Let's say it's a CSV array, and you have all that stuff. Generates this, which in itself is 62 bytes. Except if I would have had a floating point number with 5 digits after the comma, I would have had what was it, 5? So if I went 3 plus, yeah, I would have had 70 bytes. So it scales pretty horribly. Our solution, so as text is transmitted like this, the -x 2 characters are Unicode symbols. It's 84 bytes, but it's fixed within a few bits. Whatever you send, it's going to be 84 bytes. Even if your microcontroller craps out and produces something with 50 digits after the floating point number, well, it's still going to be 84 bytes, more or less. In terms of integrity, well, we use CRC16 ARC, so that's a check. In terms of encryption, AES CTR in 128 bits, it's a check. But can it run on FPGAs or like microprocessors or stuff like that? Well, the main issue would be AES CTR. In theory, research has showed that if you do use certain implementations, they can process about 12 megabits per second on a 25 megahertz board, which is pretty cool because most boards are somewhere in the 30 to 80 range. And we need less than 1 kilobit per second in theory. So also fun. Secondary issues would be the conversion to standards. Usually, most of your representations are baked in, but floating point to IEEE 754 representation, there's a pretty sequential algorithm that happens that just does binary additions, binary math. So left shifts, right shifts, and the like. And CRC16 has the exact same thing. It's binary shifts and the like. In terms of mobile development, well, for storage, if you're part of the 95% of devices that have Android or iOS, you have frameworks for preferences. You have frameworks for reading files. You have frameworks to have database systems on phones. These are all things that you shouldn't have to store on an SD card or on physical storage. So you can use these things. In terms of memory, well, you can use singletons, which are a single object instance design pattern, which sound complicated, but what they do is they basically create one instance of a memory storage, an object, which is accessible from anywhere. So you can interact, use its methods and the like. Usually it's used for database wrapping or API wrapping, the like. It's convenient. The problem is that you don't know who is requesting the information, what segment of your code is requesting it. And asynchronicity, which solves concurrency issues, which would basically mean that if you're reading a file, reading a database, or querying an API, you don't do everything at the same time and have a blockage. What you're doing is you're doing it on the side and you're waiting for things to happen. And this allows you to sequentialize or serialize operations that take a lot of time. So let's go now live to Studio. So let's take an information security professional, a developer, and a manager. And these are things I've heard. So in this case, I'll be the information security professional, although I'm not an InfoSec professional. It's an app. It needs to look good. We'll sort out the data later. Yeah, big issue there. Your service is bound to change, and your UI is probably going to crap out when you're thinking about that. So yeah, adapting a UI to a service is probably easier than adapting a service to a UI. Worst case scenario, you can parallelize. Our data persists for 1 second. What's the worst that can happen? Well, for example, when you're transmitting data via Bluetooth. Well, if you know about ward driving, which was a thing that was done in the 80s and 90s to get access to enterprise wireless networks, you have access. You have the same thing for Bluetooth. The Shmoo group at DEF CON 11 in 2003 did an entire presentation on Bluetooth word driving. It's a thing nowadays. So yeah, it's something we need to think about. We don't use application IDs for location data if you're using location. What do you mean they can be tracked? Well, I'm just going to point you to New York Times 2019 privacy project, where they took location data aggregators from your ad services and everything, and punched everything into a machine. And they were able to find people at the Pentagon, at the White House, people that shouldn't have probably have been able to be tracked by just tracking them from their homes and then following the dot around. So pretty fun. So yeah, location using and transmitting devices can be traced. The developer saying the manager can't coordinate the idea with the rest of the task. An idea being, cybersecurity suggestion or some form of suggestion. So first, that's going to get you to yell internally. And secondly, you can use a mockup-based workflow. And once the service is built, you switch the data calls from mock calls to actual service calls. That's pretty cool. Develop a ton of apps and have deadlines. Well, define a template project, a baseline project with minimal services for API calls, databases, Bluetooth, location, etc. It's easier to strip content away than add content when you need it. Also, if you do it correctly, it allows you to spread your updates correctly to every single app you do. In conclusions, IoT is the stuff of nightmares. Don't tell your CISO about IoT. Improvements for the moment aren't standards. They're improvements. It's not ISO certified. It's really horrible for the moment. Security is a matter of being consistent on all fronts. You can have the best web app security. If you have shitty IoT security, you're done for. And my own 2 cents are to have an InfoSec professional assigned to a dev team because it's going to matter at some point. It'll help you from snowballing into vulnerability hell. And since IoT is now a networking backbone, it's a great part of the networking. We need to think about that. My talk is available under CC by SA, which basically is an open license. Have fun. Just credit me. And I'd like to thank all these fantastic people on the screen, and you can ask me anything.
Thank you, Nicholas. That was really good. I will see if we have any specific questions.